Welcome to Math 30-1, where we are in Chapter 5 looking at logarithmic and exponential functions. And in today's lesson, we're going to look at solving equations, both logarithmic equations and exponential equations. And here we will begin today by looking at these three warm-up questions. Not too challenging, should be relatively quick to do. We have this warm-up just to evaluate log base 5 of 20. You can plug it into your calculator. If your calculator works in base 5, then feel free to do that. Otherwise, you can use the change of base rule in order to evaluate. The answer you get from number 1, you're going to take and you're going to plug into the exponent for question number 2, and then you're going to explain, well, what happened in those first two questions? Why did you get the result that you did? So pause the video at this point, and once you finish these three questions, you can restart the video. Well, here you can see my answers for question number 1. We wanted to keep all the decimal places, so I just put the dot, dot, dot there. And I took that whole value, plugged it into the exponent for question number 2, and my answer for number 2 is 20. And what I wanted you to observe here, and probably you did, is that my final answer here, this output, is the same as the input that I initially put into question number 1. Why does that happen? Well, it's because these two operations are inverses. When they have the same base, logarithms and exponential expressions are inverses of each other. So when the output from the base 5 logarithm becomes the input for base 5 exponential expression, the two operations undo each other. And we've looked at that a number of times in previous questions and examples and explanations, but I just wanted to re-emphasize how these two inverses work together. And it's a key idea for us to be able to solve exponential equations where our variable is in the exponent. But before we get to exponential equations, we'll start with logarithmic equations. Logarithmic equation is an equation that contains the variable or the logarithm of a variable. In other words, the variable is inside the logarithm being operated on by the logarithm. So we want to solve these equations algebraically, and then we're going to verify the solution. As we look at question number 4, I have two logarithms on the left, and what I can do is I can use that law of logarithms to combine these into a single logarithm. So because I have addition of logarithms, and remember a logarithm is an exponent, so I'm adding exponents. When do I add exponents? Well, when I had the same base, I have the same base for these logarithms, and when I was multiplying the powers. A logarithm operates on a power, so the left side is equivalent to log base 3 of 9x, the first power, times the second power of x, so that'll give me a 9x squared. And that will equal the right side, which is a 4. Now we can use what we understand from the relationship between exponential and logarithmic equations to rewrite this logarithmic equation in exponential form. So here my base is a 3. Remember the logarithm is an exponent, so the exponent is a 4, and this is equal to the power that the logarithm was operating on, the 9x squared. And now we have a relatively simple quadratic equation to solve. 3 to the 4th is 81. Divide both sides by 9, and I get 9 is equal to x squared. And when I square root both sides, I will get x is equal to positive or negative 3. So remember that when we introduce this square root sign to undo the squaring, with it we also introduce a positive or negative because there are two square roots. Now we're asked to verify. So again, when we're verifying, just like with previous courses, we'll look at our original equation and we'll replace the x's with the positive 3 and the negative 3. So I have log base 3 of 9 times my x value plus log base 3 of that x value. And I want to see, is that going to equal 4? Well, let's begin by substituting in the 3 to see if we'll get the two sides equal to each other. Well, 9 times 3 is 27, so I have log base 3 of 27. Right away, I'm going to rewrite that as 3 to the exponent 3, right? Because 27 is 3 cubed, plus log base 3 of 3. Is this equal to 4? Well, the logarithm says if I was to rewrite the 27 as a power base 3, which I did, the value of the logarithm is the exponent. So this exponent is the value of the logarithm. Here I have an exponent of 1, so there I have a plus 1. Is that equal to 4? Yes, it is. 4 is equal to 4. And so my solution of x equal 3 is perfectly acceptable. Well, let's repeat this process, but now let's substitute the negative 3 in place of the x. And immediately, well, hopefully fairly quickly at least, we recognize that there's a bit of a problem here because I have log base 3 of negative 27 plus the log base 3 of negative 3, and I want to know, is that equal to 4? Well, remember, when we look at a logarithmic function, and if we think about the graph for a logarithmic function, here we'll go. So if I was to look at what does the graph of y equal log base 3 of x look like, because my base is bigger than 1, my graph will start down here and then it's going to curve up to the right and kind of go like this. And my domain would be that my x value has to be greater than 0. Well, here I have an x value that's less than 0, x value that's less than 0. A logarithm can't operate on that. It's like if we were to square root a negative number, we wouldn't get a real value. So in this case, we'll have to say that x equaling negative 3 is an extraneous root. And so the only solution is x equal to 3. And we'll just say that is a real root. So we have just this one solution from this first equation. So that raises the point that we have to be careful with logarithmic equations because there are limitations on what we can take the logarithm of. So we could just always verify at the end, or with number 5, what I could do right at the very beginning would be to say, well, what are the restrictions on the variable? So inside here I have a 6x, so 6x has to be greater than 0. All right, I can't take the logarithm of a negative, which means that x has to be greater than 0. From the second logarithm, x plus 6 has to be greater than 0, which means that x has to be greater than negative 6. And from my third expression, I have the x minus 1. That has to be greater than 0, which means x has to be greater than positive 1. What values for x make all three of these inequalities true? Well, if I look at that middle one, where x is greater than negative 6, I could say, well, negative 5 satisfies this inequality, but negative 5 doesn't satisfy the other two inequalities, so this one is not the most restrictive. Here I have x is greater than 0. Well, what about a half? A half is greater than 0, but is a half greater than 1? Nope, so that's not the most restrictive. So I want to keep this as the restriction on my variable. And I'll keep that in mind as I go through and solve that my x value will have to be greater than 1. And now let me clean this up so that I have space to do some work. As we did with question number 4, I want to start with combining the two logarithms that are on the right side of this equation. So my left side I'll just leave as the log of 6x, and the right side I'm adding logarithms, which means I'm adding exponents. So that happens when I'm multiplying their powers. So the x plus 6 will be multiplied to the x minus 1 inside that single logarithm. Now this equation is a little bit different than the first. In the first equation, I had a logarithm equal to a number, and so I rewrote it in exponential form. For this question, I have a logarithm equal to a logarithm. Both of them are base 10, and so I'm going to do this question similar to when we solved exponential equations, where we could rewrite both sides as powers of the same base. In this case, I have a log base 10 equal to a log base 10. So my bases are the same. My exponents are equal. Remember, a logarithm is an exponent, so the two logarithms are equal, meaning the two exponents are equal. That means that my two powers, the 6x and the x plus 6 times x minus 1, must also be equal. And I'm going to expand that out right away. So I'll have x squared minus an x plus a 6x will give me plus 5x minus 6. And then collecting all the terms to one side, we will get x squared minus x minus 6. Quadratic equation, so let's see if we can factor it. It multiplies to negative 6, and we'll add to a negative 1, well, a negative 3 and a positive 2. So we get the solutions that x could equal a positive 3 or a negative 2. And again, some of you already remembered, oh, x has to be greater than 1 because I can't plug a negative into the logarithm. So this negative 2 value I'll have to reject as extraneous, and x equals 3 is my only possible solution. It meets this condition in the domain that we have up there, but it's still a good idea for us to verify algebraically. And we've saved a little bit of time by already eliminating one of those possible solutions. So here on my left side, I will have the log of 18, and on the right side, I will have the log of 9 plus the log of 2. Again, adding these two logarithms, I can multiply what it's operating on, so my right side, again, will give me the log of 18, and the left side is equal to the right side. So I do have that one solution where x is equal to 3. On to example 6. Another logarithmic equation, similar to what we previously did. So we again will begin by applying the law of logarithms to rewrite these two separate logarithms as a single logarithm. This time we were subtracting the logarithms, which means we need to divide the two arguments from the logarithms. An argument is something that is being operated on. So we'd say the argument for this first logarithm is x plus 20. And the argument for the second logarithm is x plus 5. So that's what we mean when we use the term argument in math. Well, now I have a single logarithm equal to a number. So this will be similar to question number 4, where I can rewrite this in exponential form. The base was 4, so there's my base of 4. A logarithm is an exponent. The exponent was 2, so 2 goes in the exponent. All of this is equal to the power that the logarithm was operating on. And then we'll go through the steps of solving this equation. And there I get a solution of x equaling negative 4. Now initially you may have some flags going off or some bells ringing or something saying, oh, x is negative, we can't have a negative value. But when we verify, notice I'll have an x plus 20, so a negative 4 plus 20, that gives me a positive 16. That's acceptable. And here a negative 4 plus 5 gives me a positive 1. That's also acceptable. So just because I get a negative value for x does not automatically mean that it will be a non-permissible value. And in fact, when we go through these steps for verifying, we discover left side equals right side, and so our solution of x equaling 4 is a perfectly acceptable real value solution. Let's look now at some exponential equations. Now you'll remember that for an exponential function, the domain is all real numbers. So we're not going to have the same issue of finding extraneous roots when we have an exponential equation to solve. Extraneous roots may show up in a logarithmic equation, but they won't show up in an exponential equation because of that domain of all real numbers. Now to solve this exponential equation, we can again switch the form of the equation. We have it now in exponential form, but if we were to rewrite this in logarithmic form, we'd say, well, the base is 4, so I have log base 4. The logarithm is an exponent, so this is equal to the exponent of x, and it operates on the power. This 4 to the x is a power, which means the 12 is also a power. So log base 4 of 12 equals x. Look at that. We finished the question. We're asked to solve algebraically, and that's what we've done, and to state the answer exactly. So far, here we have an exact value solution. We're also asked to approximate the answer to 2 decimal places. So we would want to plug this into our calculator in order to evaluate. When we do that, we get an approximate answer of x being 1.79. Now that's not the only way we could have solved this equation. So let me suggest another possibility here. Suppose instead we had taken the logarithm of both sides. So if we perform the same operation on both sides of the equation, it's a legal step in solving. And so if I was to take the log base 4 of 12 on the left and log base 4 of 4 to the x on the right, that's a legal step. Now, why did I do a log base 4? It's because my power had a base of 4 with the x in the logarithm. That's a kind of funny looking 4, but that is a 4 in the base for my logarithm. And we know the log base 4 of 4 to the exponent x, that's just equal to x. And so we get again, x is equal to log base 4 of 12. Well, we chose to use base 4 there, but we could have used any base. So what I could have done is I could have said, well, let's take the log base 10 of 12 and then take the log base 10 of 4 to the x. Why would we do log base 10? Well, historically, it's because before calculators, base 10 logarithms were calculated in a numeric way and then put into tables to make life easier for mathematicians. And then when calculators came in, initially they only operated in log base 10 or base e. So we could do this, then we want to solve for x. And what a logarithm does is it lets us take this x in the exponent and multiply it in front. Remember that third law of logarithms, where this could be written as x times the log of 4. And then we would divide that log of 4 on both sides to give us x equals the log of 12 divided by the log of 4. And if your calculator doesn't work in bases other than base 10 or base e, you would have wanted to calculate this to get that answer of 1.79 earlier, because we know that this is the same as the log base 4 of 12. So there we have 3 different ways we could have solved this exponential equation. So let's look at question 8. Now we're looking at a step more challenging because I have some number multiplied to this power. And so my first step will be to get rid of that 3. I'll divide both sides by 3, which will give me 12 equals 2 to the x plus 1. And let me use that first method again. Let's rewrite this in logarithmic form. So my exponent, x plus 1, is equal to the logarithm where the base is 2 because the base for my power had been 2, and it'll be the log base 2 of 12. And then I'll subtract that 1 over to the other side to solve for x. Now, it might be tempting here to do 12 minus 1 is 11, but remember the logarithm is only operating on the 12, so I can't subtract this 1 from that 12. This would be my exact value solution. And then if I was to plug this into my calculator, we could evaluate an approximate solution. And there we have our approximate solution and our exact value solution. Again, there are more ways that this could be written. And if your calculator doesn't operate in base 10, then what we could have done here is to use that change of base rule that says x is equal to the log of 12 divided by the log of 2, and then subtract the 1. On to question number 9. Well, question number 9 takes things another step more difficult, where we have a power equal to a power now with variables in the exponents on both sides. So rewriting this in logarithmic form is not going to be the best option. So I'll want to take the logarithm of both sides, and I can decide what base I want to use in my logarithm. Why don't I do this question, taking the log base 10 of both sides. So I'll have log base 10 of 7 to the x equaling log base 10 of 2 to the x plus 3. Using that third law of logarithms, I can bring this exponent down in front. So I'll have x times log 7 equaling x plus 3 times the log of 2. And hopefully you're uncomfortable with what I wrote. If this was a question on a test that was asking, identify the step that first shows an error, there's an error in what I've written here. What I said was fine, but the way I wrote it is not. This whole exponent needs to be multiplied to that logarithm, so I have to put the brackets in there. That's part of clear communication, and so that's essential. Continuing on with the question, I will distribute that log of 2 into the brackets, so I'll have x log 2 plus 3 log 2. Well, why am I doing this? Well, it's because I have a variable here and a variable there that somehow I need to get together to one side. And by distributing, now I have this expression that I can subtract on both sides of my equation in order to bring the x's together. So I'll have x log 7 minus x log 2, which will be equal to 3 times the log of 2. So on the left, I have an x multiplied to each of those logarithms, so it's actually a common factor that I'm going to pull out, which will leave me with a log 7 minus log 2 after I've factored it out. Now I could just take this whole bracket and divide it to the right-hand side, or I could do some simplifying first. And that introduces the idea that there are a lot of different ways that the exact value answer can be written. So let me actually do some combining here. So log 7 minus log 2 will be the same as the log of 7 halves. And let's do that on the right too. This 3 that's in front I can bring into the exponent. And so this will be the same as the log of 2 cubed. Now when I subtract, or I should say divide that bracket on both sides, I'll have the log of 2 cubed, which is the log of 8 in the numerator, and the log of 7 halves, or the log of 3.5 in the denominator. So this would be an exact value solution for this question. And if I plugged it into my calculator, I would get approximately 1.66. Now, I haven't talked about verifying any of these solutions. Because we know that x can be any real number, we know that there won't be any extraneous roots, but I can't be 100% sure that this is the correct answer unless I verify in some way. So what I would do, in this case, we weren't asked to verify, I'd probably graph or use graphing to find a solution to the equation and then compare that with my equation that I have here to see if I get the same decimal approximation. Let's continue on to question number 10. But before we do number 10, I'd like you to consider a question. Could I divide both sides by 3 in that equation and then get this new equation to solve? Take a moment to ponder that and decide, is that a legal step or is that not a legal step? Well, when we want to test whether a step is legal or not, then what I find helpful is to think about a simpler equation and then try it out. So suppose I had 3 to the exponent 4, and I know that's equal to 81. What I was thinking of doing here was dividing both sides by 3, so this 3 divided by 3 would give me a 1, that's where this comes from, and then 6 divided by 3 gives us a 2. So here, what if I divided this by 3 and this by 3? Well, I know 81 divided by 3 is 27. And if I kind of think about what I was doing here, 3 divided by 3 is 1. Is that equal to 1 to the 4th? Nope, not at all. Why not? Well, when we look at it in this form, we recognize fairly quickly that, oh yeah, if I'm dividing powers that have the same base, I subtract the exponents. So what this is equal to is not 1 to the exponent 4, but a 3 to the exponent 4 minus 1, or a 3 cubed. 3 cubed is 27. So what was written up here, not a legal step. So we can't divide out something that looks like a common factor on both sides of this equation. So let's just take the logarithm of both sides. Well, in question 9, we did log base 10. Let's pick a different base here. So here I have a base of 3, a base of 6. I could choose either one. I'm going to use base 3. So I will do the log base 3 of 3 to the exponent 2x plus 1. And I have to use the same base on the right side as well. As much as I want to use base 6, if I do a log base 3 on the left, I have to do a log base 3 on the right. And I missed out this 1 here in that exponent, but here I have log base 3 of 3 to an exponent. Since these bases are the same, the value of this logarithm is just the exponent 2x plus 1. On the right side, not quite so simple. I need to bring that exponent down in front and multiply it to the logarithm base 3 of 6. And again, I'll distribute to get rid of those brackets. Now I want to collect all the x's to one side. So on the left, I'll have 2x minus x log base 3 of 6. And on the right side, I'll have a negative log base 3 of 6. And then the minus 1. And again, I can't subtract the 1 from the 6. The 6 is inside this logarithm. On the left, we have a common factor of x that we can take out. And then we can divide out that bracketed part and take it to the right side of the equation, which gives me my exact solution. So as unattractive as this may look, this is an exact value solution. We can plug it into our calculator to get an approximate value of negative 7.13. Now getting a negative value for x here again is not a problem, because remember, exponential equations or expressions, we can have any real number in the exponent, whether it's positive or negative. So we have our approximate solution, and our exact value solution. Question number 11 takes us one more step more difficult, and this is as challenging as questions will get for us. So now we have a number that's multiplied to one of the powers. We had something like this in the previous page, but we were able to divide that 2 to the other side to simplify. Now we can't because the 2 isn't a common factor here, plus we have a power on this side. So I'm going to take the logarithm of each side, and again, I'll just go back to the old standard of a log base 10. Now when we get to this point, there's a common mistake that's made. We know that we can take this exponent here and we can bring it down in front. That's not a problem. We also want to look at this exponent here and bring this down in front. But that's a problem because this exponent of 2x plus 1 doesn't apply to this 2. So everything inside this logarithm doesn't have that exponent. Here, this logarithm was a single power. Here it's not just a single power. So I can't bring that exponent down in front. First, I have to separate this into two separate logarithms. And the way I do that, here since I'm multiplying powers, that means I can add the exponents. Remember, the logarithm is the exponent. So this is the log of 2 plus the log of 9 to the 2x plus 1. Now this logarithm is operating on a single power, and I can bring that exponent down in front. And from this point, the question is similar to previous questions we've done. So I'd encourage you to pause the video at this point, work through the question to finish it off, and then restart the video to compare your answer with mine. Pause the video now. So here you can see that I've distributed to get rid of the brackets. So this log 5 got distributed to both of those terms, and then this log 9 got distributed to both of the terms in that bracket. And then I collected all the terms with x on the left, and the terms that didn't have an x, this minus log 5, I took over to the right side to get that minus log 5, well actually a log 5 added on the right-hand side. When I factor out the x on the left, I have the log 5 minus 2 log 9 in brackets left over. On the right-hand side, just to make it so I had less stuff to write down, I combined the three logarithms together into a single logarithm by multiplying their arguments together. And then I can take the bracket to divide it over to the right-hand side. Here you can see my exact value solution. Again, I could combine those logarithms together, but I won't. And then I can find an approximate value solution by plugging it into the calculator to get a negative 1.62 as my approximate answer. Again, I could graph the original equation to find the solution as an approximation, just to compare to make sure I did my work correctly. And there we have the end of this lesson. Now, just before we move on, or stop this lesson, I have two questions, and they're related to this last one. So again, we had, this was our starting equation, 5 to an exponent equals 2 times 9 to that exponent. What if the question had been slightly different? What if instead our question was like this? Would we solve the equation in exactly the same way? Well, we're tempted not to. What we're tempted to do, again, just like we did not in the last question, not in number 11, but in question number 10, where we have this 2 in front, we kind of want to divide this by 2 and divide this 6 by 2 to give us a 3 to the exponent x minus 1. But remember, that's an illegal step. We can't do it. So if this was our equation, as much as we're tempted to divide by 2, it's not going to be helpful. So we would need to solve the equation exactly the same way as we did in question number 11. What if instead our equation looked like this? Well, what we did in question number 11 is always legal, so we could solve it that way. But we do have another option in this case where we have the 4 as the base on the left-hand side. So let me just show you what we could do in this situation. I could take this 4 and rewrite that as a 2 squared to the exponent x minus 1. And then those exponents can be multiplied together, so I get a 2 to the exponent 2x minus 2. Well, if this is equal to 2 to the 2 times 9 to the exponent 2x plus 1, I could divide both sides by 2 in this case because these two could be considered as powers with the same base. Here the 2's would cancel out. Here I would imagine this 2 has an exponent of 1. Dividing powers would mean I can subtract the exponents. So I would have 2 to the exponent 2x minus 2 minus 1 gives me a minus 3. In which case I get this equation, which is a little bit simpler than our starting equation where we have this extra 2 multiplied to the power. So that would be an option that we could do in this case, but in other cases we couldn't. So the process that we did in question 11 always works. We just have to be really careful with this 2 and with dealing with this exponent here, separating those two logarithms as our initial step before we bring that exponent down in front of the logarithm. All right, that's enough for today, a long enough lesson. There's some questions you can practice from your workbook, and we'll see you in the final lesson of the chapter.